Well, welcome back, everyone. This week and next week also, I'd like to start a series of lectures talking about how we epidemiologists use regression models in our research. Now, these are going to be very big picture, somewhat superficial lectures. They are in some ways ticklers to have you want to take more after completing this class. What I'd recommend, and I'll probably say this a few times, is that if you could take one course to complement what Marcello and I have been trying to convey, is to take a course in regression, because it's a commonly used method that we epidemiologists use for two purposes. And the first is what will be the focus of this lecture. This slide describes the two main ways we epidemiologists use regression models in our research. Basically, the main reason you'll see epidemiologists using regression is to control confounding. Now, confounding is a topic we talked about a couple of weeks ago. We talked about the concept of confounding. We talked about how you could adjust for confounding with stratification. And under stratification, we talked about two different methods: the method of weighting averages, using Mantel-Haenszel's method, or the method of standardization. Well, that method has limitations, as I'll try to show this week in these lectures. So typically, if you pick up a journal now where they have had to adjust for confounding, if you look at the method they used, 99% I suspect you'll see that they've used a regression model. And the big message I want you to take home from this series of lectures is that the regression coefficient of the exposure of interest in the regression model is going to provide an estimate of the effect of that risk factor, controlling for the other factors in the model. So the way we control for multiple confounders in epidemiologic research is we build a regression model, put in the model a term to represent our exposure of interest, put in the model other terms to represent our confounders that we want to adjust for, and then we're going to focus on the regression coefficient of the exposure of interest. And I'll go through a few examples to show you that. Just to hint at what we'll be doing in a future lecture series, we're going to talk about another mechanism, another reason we epidemiologists use regression models, and it's to predict outcomes, to build prediction rules. That's what's going to be the topic of next week's lectures. There, the regression model is going to provide not an estimate of the effect of a single risk factor on the outcome, but provide an estimate of the risk of developing the outcome, the risk of dying or the risk of developing heart disease, based on a series of risk factors. Well, that's going to be next week's topics. But now let's focus on the first one, regression for the purpose of controlling confounding, and looking at a regression coefficient as an adjusted measure of the effect of a risk factor on the outcome, controlling for the other factors in the model. Well, to build this, let's go back a few weeks to when we first talked about measures of association and just review a couple of important principles that I want to build on this week. And if this review doesn't sync well, then you might want to go back to those previous lectures and review what we talked about regression coefficients. I think it was in the fourth week of this course when we talked about measures of association. I showed you this example from your Framingham data set. I had taken your cigarette variable, number of cigarettes a person smokes each day, and from it made a categorical variable called packs. 0 meant that you smoked no cigarettes at all, you were a non-smoker. 1 represented you were a 1-pack-a-day smoker, smoking anywhere from 1 to 20 cigarettes a day. 2 represented being a 2-pack-a-day smoker, and 3 means 3 or more packs a day. And what I showed you at that time is the number of people, for example, 2,253 who were in each of these categories, 2,253 being in the 0 category of the non-smokers, 80 people being in the category of 3 or more packs a day smoked. I talked about the number of deaths that were observed during 24 years of follow-up, 762 out of the 2,253 non-smokers, pack 0 people, 36 out of the 83 pack-a-day smokers, and then at that time, we talked about estimating the risk of developing the outcome, mortality in this case. The cumulative incidence would have been 762 over 2253, or 34% for the 0 pack-a-day smokers, versus 36 over 80, 45% for the 3 or more pack-a-day smokers. But then I went a step further. I took this table and displayed it as a figure, where Basically, on the horizontal axis, we can think of this as the x-axis in this two-dimensional plane, I have the number of packs a person smoked. On the y-axis, I had the estimated risk from that previous table, and the 4 points in this plane represent the locations. The estimated risk on the y-axis, the number of packs cigarettes smoked on the x-axis for each of the 4 groups, and I noted that that time those 4 points seemed to fall in a straight line. And then we talked about remembering the equation of a straight line. In general, if you had a straight line in two-dimensional plane where y represented the vertical axis and x represented the horizontal axis, the equation for a straight line was y equals mx plus b. At least that's how I was taught the equation of a straight line. Where m, the coefficient of x, is what we call the slope. It's describing how quickly that line is going uphill or how quickly it's going downhill or whether it's staying flat. It's telling you how much your y value changes when you increase your x value by 1 unit. Well, in the previous picture, if I go back to that for a second, we had a straight line approximating the relationship between how much you smoked, packs, x, and your risk of developing the outcome mortality, y. So if y equals mx plus b, then this formula can be written down to say your risk of dying is equal to some value b0, which is the intercept of that straight line where it cuts across the y-axis, what was little b in the general formula we had on the previous slide, plus b1 times x. X now is the number of packs. b1 is your slope coefficient. b1 is measuring how much your risk is changing when you increase x by 1 additional unit, which in this case means smoking 1 additional packs of cigarettes per day. And I made at that point the comment that b1 is a very natural measure of association. So these regression coefficients are ways to capture the relationship between a risk factor, in this case packs, and an outcome, in this case the risk of dying during 24 years of follow-up. And then as the final review, we went one step further and said, what if we didn't make our y-axis the risk, but some function of the risk? And the function we talked about before then was called the logit. The logit is the log of your risk over 1 minus your risk, the log of your odds of dying. So if you wanted to express the linear relationship between your log odds of dying and the amount of cigarettes you smoked, the equation would say your log odds of dying is equal to b0 plus b1 times the amount of smoking, packs 1. So b1, again, is the slope. It's then telling you how much your y variable changes with every unit increase in x. But now your y variable is not a risk, but the log odds of dying. So as before, b1, the slope coefficient, is going to tell you how much your outcome, log odds of dying, changes when you increase smoking by 1 additional unit. And back then, when we first talked about regression coefficients as measures of association, we reviewed some basic laws of logarithms, and we said that the change in your log odds is nothing more than the log of your odds ratio. So b1 in this logistic regression model has the interpretation of being an estimate of the effect of your risk factor, packs 1 in this case, on your outcome, being represented as being a log odds ratio. So if we wanted to estimate the odds ratio, we could take just odds ratio would be equal to the exponential function of b1. And we're going to use that fact now again to build on this basic principle that regression coefficients are measures of association between risk factors and outcomes. For logistic regression models, they are functions of odds ratios, but now we're going to build on it by trying to use these models to control for confounding. And that's what we're going to do in the next section. See you then.